All right, welcome back. We're halfway through this afternoon, and tomorrow. Tomorrow will be our day of machine learning again. So this afternoon we have Professor Dave Kirkby from physics, another physicist. He's been teaching machine learning, as probably most of you know. And he's going to give us machine learning for the physical sciences until a little bit before 3, and then the last talk of the day will be Professor Pierre Baldi from ICS. All right, just a couple of things, resources that I recommend you to be aware of. One is Hanan Shen, for reasons we've talked earlier. The other is Nathan Crawford, or Director of Scientific Computing, that you probably will benefit a lot from developing a relationship with Nate if you're a computational person. And one of the most significant resources we have, really, probably the most significant, is this guy here, Jim Dow, standing there. He makes everything happen, that guy. So you should also get to know Jim. You probably need him at some point. Anyway, welcome, Professor Kirkby.
Okay, so thank you. So this is an interesting classroom. So I guess everyone can see at least one screen. It's not very big. Okay, so I'm going to talk about machine learning in the physical sciences, but I think a subtitle could be what I wish people had told me when I first started learning how to use machine learning for my research. So I'm in physics and astronomy. My research is primarily in cosmology. So my data is images and spectra of distant galaxies. Okay, so just briefly, so we're all on the same page. What do I think of as a scientist? What do I think of machine learning? What does that mean to me? So it's using machines. And what are the machines? So the machines really should be in quotes. The machines that we use in machine learning are a combination of software algorithms, so not really physical machines, computer hardware architectures, so in particular advances like GPUs, graphical processing units, that have really revolutionized what we can achieve in a useful amount of time. And then also human ingenuity. So a lot of the revolutions and the rapid advances in new algorithms that people brought up. And then the learning part. So I think learning is a little oversold in machine learning. It's not really how we normally think of as learning. Basically, the way machines learn is that they're just going to passively identify correlations, statistical correlations that are in your data. So if you think about how you learn, how a baby learns about their environment, it's very different because you actively experiment with your environment, you try things out, and you learn causal relationships. Okay, so in machine learning, there's no scope for doing that. And I'm going to go through a lot of different topics. So rather than try and remember any questions you have, just feel free to interrupt as I'm going. If you have questions, just ask me. I think it'll be more interesting that way. You're not going to remember your questions. Okay, but really I think the view I've come to is that machine learning is primarily, it's about the relationship between data and models. Those are the fundamental components of any machine learning. So there's the data that you bring to the table, and there's the model that you're going to select in order to explain your data. So really machine learning is about explaining data with models. So it's kind of a cartoon cycle of how machine learning works. So this is specifically for supervised learning. So you have some data, that's what you're bringing, and in supervised learning you also have some labels. So every piece of data, every observation has some labels associated with it, and these are the true labels. And you feed that into your machine learning algorithm in what's called the learning or training cycle. And then all of that, everything that it learns is going to be internalized in a model. So we've gone from a data, actually two types of data, the bulk of the data, and then these labels, and then we've internalized that into a model. And then once you've learned a model, then normally what you want to do is you have some new data, and then you want to use your model to predict what the label is for that new data. Okay, so it's learned kind of a mapping from the data to the labels in this training cycle, and then in the second cycle you want to predict, or machine learning we call infer, the predicted label for each piece of data. And then finally, in the third phase, this is important, is that you want to have some data which you didn't use in the training, so you held it out, where you still know the true labels. And you're going to use that to then compare what the predictions are with the true labels. So that's kind of the assessment phase. And sometimes you find things at this stage are really not what you were hoping for, and then you have to kind of iterate over the whole thing. Okay, so that's kind of at an abstract high level. But just to make this more concrete, so I want you guys to actually be the machines here and do some machine learning yourself. And so the data here, so this is a problem in my research. So these are astronomy images, and wow, that's hard to see. So what we're looking at here are pixels. These are little kind of postage stamp size images from a telescope. They're actually simulated images, but that doesn't really matter. And so the label in this case is the number of galaxies. So when you point your telescope at a point far in the sky, the galaxies aren't all laid out on a nice grid. Sometimes there'll be no galaxies. Sometimes there'll be 2 or 3. It is actually quite hard and scientifically interesting to know how many galaxies there are each time you you look at a little patch of the sky. So the label there is the number of galaxies. And so the task that I've defined here is we want to learn to predict the number of galaxies, so that label, given one of these images. So I think the quality of these images is not good enough for you to actually do this in a reasonable way, but because of the screen. But some of these examples are really clear. So there's 3 there, and actually it says there 4. So the true label there is 4. So in learning, you've got to learn, well, maybe the fact that this thing here is a little extended, that's because there's actually 2 overlapping galaxies. And so that's because I believe that galaxies are actually quite compact and round. So an extended object is probably a superposition of 2. So I don't necessarily have to have space between each of the galaxies. So that's my rationale for why that's 4 galaxies. So I'm learning. So basically I'm internalizing that kind of information into the model here. And then there are going to be some which are just 1. That's 1. That's 1. So you can see that here you learn the variety of what a single galaxy looks like, and that informs you when it comes to estimating whether there's 2 galaxies on top of each other. Okay, so then the next phase then is after you spend a little time looking at this training data. Then, so here are some tests. You can make your own predictions, and I'll let you when you are you going to share the slides with?
Yes.
Okay, yeah. So the slides actually, when you do this in the slides, if you click on that link, you can actually put in your predictions, and I appreciate that because I've kind of got already a good data set of people who have tried this exercise, and so basically you internalize this into your own model of how to perform this task, and then you can try yourself out on these 12 images right here. So that's now you're doing the second phase. And then finally, we want to evaluate. So here are those 12 test images, and the plot under each one shows you the distribution. So the green histogram, so that's the distribution of answers that actual people have given doing this exercise. The red line shows you the true answer. So in this case here, most people got the true answer. There are some examples here where the true answer was 3 galaxies, and most people thought it was 2. And for comparison, the blue histogram, so that's what a machine learning algorithm can achieve, trained on a similar a similar problem. So here we're doing the assessment both for humans and for machine learning. Okay, so if you go through this exercise, I hope this makes it concrete really what's going on in machine learning. So this is an example where machine learning can match or even exceed human performance on this task. However, the humans that I use to get a benchmark here, you're only looking at those 36 examples, okay? 36 labeled examples. However, to get the comparable performance with machine learning, you'd need to provide the algorithm with thousands of labeled examples. Okay, there's no way it can do it from 36 because as soon as you look at those pixels, you already understand the problem. You can already come up with a reasonable guess. I see 3 blobs, and the answer is probably 3. Maybe it's 2. Maybe it's 4. But the computer just sees pixels. It just sees red, green, blue values associated with each pixel. So it has no notion, no kind of already idea of what this problem is about. And it really has to learn a mapping from raw pixel values to this label, the number of galaxies. So it's going to need tens of thousands of examples, and it's going to need hundreds of passes through your data set. And so this is going to be a theme, we'll come back to this, is that modern deep machine learning really it's very greedy, it needs a lot of data, and it uses it very inefficiently. And that doesn't always make sense for physical sciences. So how does a machine learning algorithm actually see your data? So the data to the algorithm, it's just a finite set of measurements. And in general, most algorithms are going to require that you coerce your data into a 2-dimensional table. So just think like a spreadsheet. So you may have designed these wonderful data structures, and you've got this complicated database and nice hierarchy and everything. So you have to kind of throw all that away if you want to use machine learning. You have to just flatten your data into something that can be represented by a spreadsheet. So the terminology is that the columns, we call those features, and the rows are the individual samples or observations. And you might have, for example, variable length data. So like each observation has a different number of some type of object. You're going to have to either truncate that or pad that. You really have to force it into this kind of rigid 2-dimensional grid. There are some exceptions. So for example, there are algorithms that can do convolutions on images, so where they really know about the 2-dimensional relationship between the pixels, or even now newer algorithms that can work on graphs, arbitrary graphs. Also, text is an area where there's specialized approaches that can handle kind of variable length text in natural languages. But in general, if you want to be able to just try lots of different algorithms kind of in a plug-and-play way, you're going to have to coerce your data into this rather rigid format. Okay, so the kind of questions you should ask about your data to really understand how machine learning is going to see it. You want to ask for each column here, is it categorical? Is it discrete? Is it continuous? You want to ask, is the ordering of the samples significant? So could you just permute the rows in here and that wouldn't mean anything? Or is there actually a natural ordering to the data? Okay, generally, most algorithms will assume that there's no significance to the ordering of the rows here. So there's no concept of kind of time in your data set. Are your samples statistically independent? And if they are, even if they are they drawn from the same distribution? So usually we assume both of those things in machine learning. What are the uncertainties? So each number here, if it comes from a measurement, you probably have some idea of the uncertainty. And it's quite a challenge to feed that information about the uncertainty into a machine learning algorithm. Is your data binned or unbinned? That will affect the uncertainties, for example. And also another important thing is there a natural concept of a distance measure between your two samples? So like if I have one observation taken yesterday and another observation taken today, can I quantify how similar those observations are? Okay, that turned out to be a pretty important concept in a lot of algorithms, having some measure of the similarity between two different observations. I'll talk about that more. Remember to stop. Okay, but of course your data is special. Machine learning treats ad clicks exactly the same as the data that you collected painstakingly with some state-of-the-art instrument. Okay, so here's one of the instruments I work with. This is a camera for a telescope being tested in a clean room. You can tell there's a lot of care and attention going into getting that data. But a lot of machine learning is just applied to almost random people clicking on ads. So how is your data actually special? Does that really matter? So I think that scientific data really does have special attributes, and unfortunately the current machine learning methods do not recognize that or take advantage of it. And so in particular, I think the most important thing is that as scientists, we are producers of data, not consumers of data. Right? In industry, most of the machine learning treats data as just something that you consume. Okay, people are clicking on ads out there, making Google searches, and you're just going to consume that data. But we actually produce our own data. We design experiments and surveys, observation protocols. We think carefully about calibration. And so there's a lot of stuff, a lot of process that goes into optimizing or trading off statistical versus systematic uncertainties. And so we very deliberately produce our data. But it's hard to really take advantage of that in a lot of machine learning algorithms. And also our data generally measures physical processes. So what does that mean? How is the fact that it comes from a physical process different from an ad hoc? So often you know a priori what the random errors are, the source of systematic uncertainty or statistical uncertainties in your data are, because you know underlying, it's either a photon counting detector or it's measuring some sort of current, electron, shock noise. So you have a kind of a first principles understanding of the uncertainties in your data, and you'd like to use algorithms that are going to be able to use that information intelligently. And then finally, our data, it's measuring physical quantities, so it generally will have dimensions and units, and those are important, and we'd like to use those intelligently. Okay, so now I was talking about data there, and I want to talk a little bit about models and how machine learning thinks about modeling your data. So all algorithms, whether it's explicit or not, they use some sort of model to explain your data. And so a model is going to learn to explain your data by adjusting some parameters. It has lots of internal parameters, and it's going to adjust to those to find the best way to explain your data according to some metric. And so the relative importance of the model and its parameters depends really on the task that you're trying to perform. So for example, if your task might be to estimate the age of the Earth, estimate the number of galaxies present in an image, or classify pet photos into cats versus dogs. So let's take the first one. So estimating the age of the Earth. So there, do you think it's the model or the parameter that's most important? So is the age of the Earth a model or a parameter?
Parameter.
It's a parameter, yeah. So fundamentally, this is really about a parameter. The parameter is the main thing. The last one, classifying pet photos into cats versus dogs. So the state of the art does this really well, but it uses millions of parameters. So do you think the values of those parameters are individually going to be interesting? No, generally not. No. It's making a binary decision, but because it's working from raw pixels, really it's a very complex model, even though the outcome is something very simple. And then this example in the middle is sort of is intermediate. It really depends on what you're going to do with this. Okay, so but I think an important thing to remember here is that when the parameters are interesting in a scientific task, generally so are their uncertainties. Okay, so the way I think of this is there's really one process in machine learning, but there's just different perspectives. Okay, so we're always starting with data. We provide data we'd like to understand, explain. And that data, unless it's just random numbers, it has patterns. And so really what the data brings to the table is these patterns. And then there's two kind of different ways of thinking, different perspectives on what you're going to do with that data. You can either train a model on the data, or else you can fit the data to get some parameters. But I think that these are it's really the same process. It's just different. I mean, you've got data, and you've got models, and it's just different ways of kind of thinking how the patterns are going to flow forward to the final result. When you talk about training a model, that's generally because what you want at the end is you want something that can generalize to new data that it hasn't seen before and can predict, for example, that new photo you've taken, is it a dog or a cat? Okay, but often, if you're interested in say, inferring the age of the Earth, that's more about quantifying what you've observed and interpreting it. So you're not trying to develop an algorithm that can then tell you the age of some new planet. You really just want to know the age of the Earth. Okay, so there, the focus is on parameters and especially their uncertainties. But parameters and the model are really just the same thing. The parameters are the internals of the model. So these different perspectives have names. So when people talk about data science, what they mean is it's really, you're kind of more focused on this part of the triangle here. You're really more focused on the patterns on the data. You're living much closer to the data. Machine learning is really more about training, generalization, prediction. So focus more on the model as the fundamental thing. And then statistics, which is a lot of what we do in classical data analysis, is around that here, where you're more focused on the parameters. And the model is just a way of defining the parameters. Okay, but an important point I want to drive home here is that estimating parameters, whether it's with chi-squared, maximum likelihood, or Markov chain Monte Carlo, that is machine learning. Okay? It's all part of the same flow. That is machine learning, but it just has a different emphasis. So maybe you've already been doing machine learning all this time. Okay, so this is a humorous kind of comparison between statistics and machine learning from Stanford. So it's kind of like a glossary. So in machine learning, they call it weights. In statistics, they call it parameters. Learning, fitting, generalization, test set performance. And then something response at the bottom response. So a large grant in machine learning is $1 million. A large grant in statistics is $15,000. Nice place to have a meeting in the French Alps or in Las Vegas in August. So I can relate to this because my collaboration meetings are in Tucson in August. So. But the point is that there's this kind of a language and a culture, jargon differences, but they really are not so good. So we talked about how the parameters are kind of the internals of a model, but models also have hyperparameters, which by definition are the things that you do not learn from the training data. Okay. So, these are things that you either have to set them by hand. Okay, that's easy, and that's usually what people do, but that's always going to be biased. You set it by hand, and then how does that affect the final result you get? Maybe if you had chosen different options, you would have got a different age for the Earth. The alternative is you can learn them using a second independent data set. Okay, so that means you have to have a whole other data set from other than the one that we're using for learning or training, and then you'll use this for a technique that's called cross-validation. So that's a better approach, but it's very expensive. Now you need twice as much data. Or effectively, you're only going to be using half of the power of your data to learn the parameters that you're interested in. Okay, so neural networks, which are really would have driven the modern revolution in machine learning, and you'll be hearing a lot more about them in the next talk today. So neural networks are models. Okay, they're not usually presented that way, but they are just another type of model. So here's a sketch of a neural network. So these are the layers of the network. We call it a network because things are connected together. The data flows in to the left. So the numbers in your data are just, so basically each row of your spreadsheet is fed into one along to these nodes here. And then the values just flow forward from left to right through the network, and then what comes out are the predicted labels. So a neural network is really it's a complex thing, but it has very simple building blocks. Each one of these nodes is just doing some linear algebra. It's taking the inputs, multiplying them by a matrix of weights, and adding a vector of offsets or biases. And then so that's just linear algebra, and then it gets wrapped in a mildly nonlinear function, and it's that mild nonlinearity which really gives all the power to neural networks. And so the colors here represent the strength of connection between any two nodes from one layer to the next, and that's encoded. That's the values in this weight matrix. So the parameters then are explicitly then all the weights and the biases. So each layer here has a separate weight matrix and bias vector. In modern deep learning applications, you very quickly get up to millions of parameters. You also have lots of hyperparameters. So the hyperparameters are a little less obvious, but just the choice of the number of layers you have here, that's a hyperparameter. You don't learn that from your data. You basically just decide, this is the architecture that I'm going to use for my neural network. And also the number of nodes in each layer. What exactly the activation refers to this nonlinear function here, exactly what function you choose there. So those are all hyperparameters. So neural networks are often used with a number of parameters that's much greater than the number of data points. Okay? So that should be mathematically impossible. But in fact, that's the regime in which deep learning often operates. And so the reason that works is partly because of some randomness or stochasticity that's deliberately introduced when you're learning the parameters from the data. So this is an example of kind of a fundamental technique in machine learning, something called stochastic gradient descent. So this is a simple example. We just have a two-dimensional surface. We're trying to get to the minimum. We start out here, and instead of just efficiently always going downhill, we deliberately take a bit of a drunken walk down here. So that's the stochasticity. Usually the way we do it is that instead of looking at all of the data to calculate each update, we just use a random fraction of the data each time. So that's the stochastic part. It speeds it up, but it also has some important theoretical advantages, and that is that it provides a form of regularization, which is basically a way of kind of cheating and allowing you to solve something with many more parameters than the data points, because you basically bias your solution to something that has certain properties, some sort of regularity or smoothness or compactness. And in the Bayesian framework, we'll talk about in a minute, that would be referred to as priors. And neural networks generally have way too many hyperparameters to optimize in any sort of rigorous way. So often people just say, okay, I'm going to use 4 layers because that's what they did, and they just stick with that. And then, but if you look at where the breakthroughs have come, where the new architectures, the new ideas come in neural network architectures, it's something that people somewhat cynically call grad student descent. And what that means is it's a play on the stochastic gradient descent. And the idea is that if you throw a lot of graduate students at the problem, that each one of them kind of explore a different architecture. One of them will probably hit on something that's going to be a great idea. So. Okay, so in the physical sciences, again, just as with kind of our data, I think is unique in ways that are important to recognize. Our models, the models that we would like to use, are also, I think, have some features that are not well captured by in machine learning right now. So specifically, so the models that we'd like to use, should be traceable to there's some underlying physical theory. We're measuring physical processes, and there's an underlying physical theory explaining those processes. So the models that you use, you'd like them to be constrained by theory and also previous observations. The parameter, because the models are traceable to physical theory, the parameters are not just arbitrary things which you don't care as long as it works. The parameters themselves are often the most interesting thing to come out of your process. The uncertainty estimate on a parameter is often just as important as its value when we're using machine learning for scientific tasks. So that means that you should generally prefer a model that recognizes, has a concept of the uncertainty in your data. And often that it's when you look at the documentation, that's just referred to as weights rather than uncertainties. And then also one that's going to provide some sort of output parameter uncertainty. So there aren't very many algorithms that really do that. And then, of course, the physical world has many symmetries. We're measuring processes in our world with symmetries, or related to conserved quantities. And so you should prefer models that have the relevant symmetries built in. Otherwise, the machine learning has to just kind of blindly discover or stumble across these symmetries. But you can imagine your model would be much more efficient if you knew about the symmetries to begin with. So the symmetries, how are symmetries actually incorporated into machine learning? So there really is no general framework for imposing symmetries on a model. So let's say you know that the data you're collecting is rotationally, you have images and they're rotationally invariant. And so you'd like to somehow make a more efficient model that has that baked in somehow. But there is no general way of doing that. And so instead, what people do in practice is they use something called data augmentation. So instead of imposing the symmetry on the model and making it more efficient, they add, multiply many times the amount of data that you throw at the model. So you have a model that has no concept of the symmetry, and you just impose the symmetry in the data. So here, for example, if we have an image of this dog here in our original data set, instead of just feeding it that one image, we're going to feed it 8 images. And so each of these 8 images has a different transformation applied. So this one, for example, is just flipped left-right. And so if every time it sees one image, it also sees the flipped partner, then just the data, it has no way to differentiate between those two states. So this is cropping, resizing, slight rotation, zooming, changing the brightness, the contrast. So this is all done as a standard thing in machine learning. But it's very inefficient because you only need the one image to start with, and now your algorithms have to deal with many times the volume of data. So there is one special case that's important, and that's convolutional neural networks. So they apply convolutions to your data, normally working with images. So those, they weren't really designed for this, but a nice feature of those is they are translation invariant. So if you have a problem, kind of a vision image processing problem, and you want it to be translation invariant, then those work. And the reason that was important in vision processing is if you want to have an algorithm that can find the faces in an image, you don't really care where in the image the face is. So the algorithm should work the same way, whether the face is in the top left corner or the center. Okay, so what are the broad types of machine learning? So the first is when I walked you through that example with estimating the number of galaxies, that was supervised learning. But unsupervised is probably a more basic type of learning. And in unsupervised learning, you treat your data called X holistically. What I mean by that, so here's your data set, is that you treat all of these columns on an equal footing. And you're just trying to learn what the patterns are in the data without giving any preference to one column or for another. And so in statistical language, what you're doing is you're trying to estimate the joint probability distribution of the data, P of X. And then supervised learning is where you consider some features of your data as labels. So let's say we'll call this last one here, that's the label. So it's kind of arbitrary. You can just designate any feature or column in your data set as a label. And then you can say, well, I'm going to supervise my learning with that labeling. So it means I'm going to learn how to predict that column for new data that I haven't seen yet. Okay, so in the galaxy example, then all the pixels in those images would be these columns here, and the last column, my label column, would be the true number of galaxies in the image. So in a statistical language, then, in supervised learning, you're estimating a conditional probability, the probability of the label given the rest of the data. And you do that on a row-by-row basis. So I want to spend a little time talking about unsupervised learning, because I think that's where a lot of the interesting work has been happening lately, and I think there's a lot of scope for using this for solving scientific problems. So some examples of what do I mean by unsupervised learning tasks? What kind of problems can you solve with supervised learning. So a really important one is dimensionality reduction. So you've got some high-dimensional data set, and you'd like to figure out how to represent it in a much lower dimension, so just more compactly. So you want to transform from the features, the raw features in your data, to a more compressed, efficient set of features. And in machine learning, those would be called latent features, because they're not the raw features, but they're kind of latent in your data. So that's a standard unsupervised learning problem. So another one is generative modeling. So that is how can you interpolate or extrapolate from, you've got some small data set, and you'd like to be able to generate new examples which are drawn from the same underlying distribution. Okay, so for example, I might feed it 1,000 images of different galaxies, and I want it from that to learn what the distribution, the probability distribution on galaxies, so that it can sample from that and generate new galaxies that it's never seen before. Okay, so it's basically kind of ingesting some population of data, and it can then generate new members from that population that it's never seen before. That's generative modeling. And then probabilistic modeling is kind of the other side of that coin. So you give it a reference data set, and now when you give it a new, instead of generating new data for you, it's going to be able to take in data it hasn't seen and tell you what is the probability that that data came from the same population as the training data. So the same thing in the diagram here. So here is some data, and a generative model would have some internal parameters, and it would be able to create new data for you. And a probabilistic model would take in data, and it would tell you the probability of that data coming from the training set. Okay, so they're closely related to each other, generative models and probabilistic models. And from a Bayesian point of view, which we'll talk about more in a minute, so these parameters, you're allowed to think of your parameters kind of on an equal footing as the data. Parameters are random variables. And so that means that it's sometimes actually useful to take this one step further and to have both a generative and probabilistic models of your parameters themselves. Okay, you're not limited to just generating data and estimating probabilities of data. You can also generate parameters or estimate the probability of parameters. And this is generally what we like to do, right? If our task is to estimate the age of the Earth, what we want is we want to estimate the probability of the age of the Earth given some data. So that's a statement about probabilities on parameters. And then the parameters of these things then are hyperparameters again. Okay, so as you're getting into this field and thinking about how you can use machine learning in your research, I think it's important to be aware of what the standard benchmark problems in machine learning are today. And so these generally focus on things to do with vision and also natural language tasks. So examples of a benchmark process or a problem would be to answer the question, is that, given an image, is that a cat or a dog? Or even more specifically, what breed of dog is it? So that would be an image classification task. There's been an enormous amount of work on that. Given an image, where are the people, the cars, etc., in a street scene? That's something that's getting a lot of interest for its surveillance applications, tracking people in airports. It's also important if you want to be able to make a car that can drive itself. You need to see where the people are, the cars, street lights. In natural language, so given a certain phrase in one language, translate it into another language. That doesn't seem like a machine learning problem, but in fact, the best performing algorithms for translating from most language between most language pairs is just pure machine learning. There's no linguistics or any kind of expert knowledge in the best algorithms at the moment. Another one is given someone's written a restaurant review, and you'd like to use machine learning to classify that review as positive or negative. So it's what's called sentiment analysis. So something that humans are very good at is actually, when you start thinking about how you write a program, teach a computer how to do that, it's actually a very hard problem. but that we can do that really well now. So I think a really efficient way to jumpstart getting some machine learning into your research is to learn about these benchmark problems, things that are really solved problems in computer science, and to identify which problems in your research map most closely to these well-studied problems. And something that people in machine learning do really well is that they curate these great benchmark data sets. And so a lot of the progress, I think, in the machine learning community is that they have these very standardized data sets that have been studied many times. There's thousands of papers referring to all of these standardized data sets. They're very well documented. They're easy to download. So, for example, the classic one is something called MNIST, which is just 70,000 rather low-resolution grayscale images of handwritten digits. So this is a great algorithm for the Postal Service, so they can automatically read off the zip codes off off the hand-addressed envelopes, and that's actually what drove this data set. So their labels are just 0 through 9. So a lot of papers. Whenever you develop a new algorithm, the first thing you have to do is try it on this MNIST data set. So another one is CFAR10. So there's these slightly larger images, and these are little crops of natural images. So there's only 10 different categories here, and airplanes, cars, birds. Pretty general categories. So anything that's not one of these categories, there'll be no images of that. And surprisingly, if you train an algorithm that can do a good job of recognizing, accurately identifying which of these categories one of these images corresponds to, then you will have a really good starting point for solving a whole bunch of other vision-related problems. So that's something called transfer learning. You basically train on a benchmark data set and then transfer you only have to change slightly the parameters in the last few layers in order to adapt it to a whole range of different problems. That's transfer learning. And then kind of the state of the art for vision stuff is this thing called ImageNet. So these are much larger and more realistic images. They have 1,000 different categories, including 90 dog breeds. Okay, so that seems pretty excessive, but it means that there's a lot of machine learning algorithms there that can instantly tell you recognize 90 different dog breeds. So far exceeding human is my performance. And so, so what's the lesson here for us? So first of all, if you are doing algorithm development work, you should test it on these existing data sets. But also, you should consider curating a public data set for your machine learning problems. So if you want to build a community within your research area of people looking at machine learning approaches, then a great way to jumpstart that is for you to actually publish your own public data set. And actually, we have at UCI, there is the ICS department has an archive that's kind of people use worldwide to get public data sets. So they have machine learning archive. Okay, so here's a question for you. What is the language of machine learning? C++, Python, JavaScript, Swift?
Python.
So most machine learning practitioners are using Python today. However, that's a little unfair. That's a trick question. The language of machine learning, it's not a computer language. Okay? Machine learning doesn't happen by you talking to the computer. It happens by people communicating with each other and kind of developing ideas and communicating ideas. And so really the fundamental language of machine learning is statistics. So here is just an excerpt from the introduction of a classic paper, all over 5,000 citations. So this is the paper introduced something called variational autoencoders, VAEs. It's kind of a buzzword in machine learning. It's an unsupervised learning technique. And this is just full of statistics, probability distributions, we have distance measures. And this actually, the second author here was a professor here at UCI. Okay, so what this means is that if you want to get into machine learning, you're going to have to brush up a little bit on your statistics. So I'm going to give you just a quick primer then. And I think the right place to start in the statistics that's important for machine learning is understanding a Bayesian way of thinking. So Bayes' rule, have you heard of? So it's just derived from a definition or even just axioms of probability. And so it's something that's entirely non-controversial. So it's a statement about probabilities like this. Okay? So you've probably heard that there is some controversy over whether Bayesian statistics is the right thing to do or frequency statistics. But there's absolutely no controversy about this relationship right here. This is just axiomatic and probability. So the controversy is about what constitutes a valid probability. So for example, here's two statements, and so people differ on how they would answer the question, which statements can we assign a probability to? So the first statement, the fraction of heads is between 49 and 51% when I flip this coin. Or the age of the Earth is between 4.5 and 4.6 billion years. So can we agree which of those statements is more interesting? I mean, what would you rather, as a researcher, what's more interesting to get the answer to? The second question, right? Okay, but depending on your perspective, you may not agree that you're allowed to assign any probability to the second question. So there's two extremes. I think most practicing scientists are not really at either extreme, but somewhere in between. But the extremes are, from a frequentist perspective, you would say that the probabilities can only be assigned to some repeatable, infinitely repeatable process. Okay? And so that allows you to make very objective statements about probability, but for statements that are inherently uninteresting, I think. So like the coin, if you actually have the coin in your hand, and you can just flip it an arbitrary number of times, if you flip it 1,000 times, you're going to be able to measure a probability of heads in a very objective way. However, a Bayesian, at the other extreme, would say you can assign a probability to any statement. Okay, but the price you pay for that is that you necessarily are going to have to be quite subjective in assigning probabilities to interesting statements. So why can't you come up with a frequentist probability for this statement here? The age of the Earth is between 4.5 and 4.6 billion years. How many Earths do we have? Okay, so there's no infinitely repeatable process that you can do to just tabulate different age of the Earth and then to see how often they fall between 4.5 and 4.6 billion years. Okay, so that's obviously a problem for what I do too with cosmology. We only got one universe. Okay, so the way that a Bayesian would apply Bayes' rule is in this way here, and there's a lot. I think a lot of what makes the papers hard to read and just kind of makes Bayesian statistics seem inaccessible is there's confusing notation that we don't see in calculus, for example, or vector algebra, and there's also confusing terminology. But if we just break it down, so this is the same non-controversial rule I gave you before, but now plugging in the terms that a Bayesian would use. So this is a fundamental object here that Bayesians and frequentists are both pretty happy with. So it's the probability of the data, and that bar we read is given, probability of data given a model. And we need to multiply that by the prior, which is just the probability of the model. That's inherently a subjective thing. So this prior here is what a frequentist would object most strongly to, because it quantifies our prior degree of belief in the model before you've seen any data. So you have to kind of, before you see the data, you've got to think and write down on a piece of paper, this is how much I believe in this model. Okay, or if more quantitatively, this model would be like a parameter, and so you'd have to say, what is my degree of belief that the parameter has different values? You'd have to make sketch a probability distribution for the parameter before you see any data to measure. And then the thing on the left, which is what you want to publish, is the posterior, the probability of the model given the data. So the model here would be that the age of the universe is, or the age of the Earth has some value, given the measurements that I took. Okay, so that's fundamentally what science is about, getting that posterior. And then this thing down here, the evidence is kind of more of a technical thing. It's just a normalization constant. You just need to sum all of sum the numerator for all of the possible models. Okay, so each of those terms has a name and have a history. But really, I think the way to think about Bayes' rule and the way that Bayesians use it is it tells you how to learn a model from data. So this is just machine learning again. Okay, so if this is just a formula that tells you how to combine optimally the new information you've got from your experiment with the prior information, which is going to be a combination of your subjective beliefs, but also from previous experiments that have relevant data. So how do you optimally combine those two things to update your knowledge, to give you your new model? And that's exactly what Bayes' rule is. It's a rigorous, optimal way of combining new information with prior knowledge. Okay, so just to give you a personal perspective on how I think about all of this stuff. I think, personally, I think you should always use Bayesian statistics to interpret your data. Okay, it's going to give you the best interpretation. I think it's unavoidable that if you want to draw useful conclusions, you're generally going to have to make some subjective choices. I don't think that's avoidable. And given if you accept that, then you might as well use a framework that allows you to really make explicit where the subjective input comes and allows you to quantify things. And it's also you're laying it out more transparently for other people reading your paper to understand what assumptions you made and how they propagated through. But on the other hand, I think it's important that you make it easy for other people in your field to reconstruct your likelihood. Okay, so specifically what I'm saying is that this is what you're going to put in your abstract, the posterior, but you need to make sure that the thing you need to share with other people is the likelihood. That's how kind of the research moves forward. And the reason for that is the likelihood is what encapsulates the new information that your experiment has provided. So that's really the thing, the object, that is going to let other people compare with your data, making different assumptions. They shouldn't have to make the same assumptions that you made. So that means that you should use simple priors in your own analysis that are easy to back out so people can get the likelihood, or even better, actually just publish the likelihood as a piece of code or as a data file. And then, in general, I think it's always important not only just for the reproducibility of your results, but kind of to allow your results to be incorporated into the field. It's important to release both your data and your code with the paper. Okay, so I just want to say kind of another area of statistics that's kind of unique to machine learning is the similarity measure. So these play an important role. A lot of interesting machine learning methods have this concept of the closeness or similarity between two probability distributions. And so things like variational inference, variational autoencoders, generative adversarial networks. So, if you've done any reading in machine learning, you've heard of these kind of buzz terms, VAE, GANs. And so if you want to understand the theory of these things, it's important to understand these different similarity measures and what the trade-offs are. So just to give you a cheat list for getting started on this, so probably the most important one is something called the Kullback-Leibler divergence. It has a weird name, and it's also a weird mathematical object. It's not really a metric because it's not symmetric. So it basically says that the distance from me to the chair is not the same as the distance of the chair to me. So, but it turns out to still be a useful thing. It's related to the mutual entropy of distributions. There's something called the Wasserstein metric, which is getting a lot of interest. And this is actually related to the energy cost in taking, if you visualize a probability distribution as kind of a pile of earth, and you've got two piles of earth, so those are your two probability distributions. So the Wasserstein metric is actually related to the cost, getting a shovel, the energy cost of with a shovel, transforming one pile of dirt to look like the other pile of dirt. Nice physical sciences, that's a nice physical picture. And then there's this thing called the Jensen-Shannon measure, which is actually, it fixes the non-symmetric problem with this KL divergence. And it's a way of combining them to make something that's symmetric. So it turns out that this KL divergence is really fundamental to these variational autoencoders. And this symmetrized Jensen-Shannon is fundamental to GANs. Okay, so So I think I'm allowed to say this, but although this is about machine learning is not always the best tool for the job. So it's important to be aware of that. But of course, it's fun to learn about machine learning, and it may actually help you get published in trendy journals. But you should just recognize that sometimes the traditional methods that people are already using are nearly optimal. And what that means is that they're already squeezing out all of the available information in your data. So unless you can bring new data to the table that actually has more information in it, there's no, even if you have a method that in principle is more powerful, there's no new information to be gained. And also, you should be aware that as you go to fancier and fancier machine learning methods, you're generally going to be sacrificing interpretability. And the latest deep learning methods are notoriously opaque and non-interpretable. And so you should ask, is there a more interpretable method? So good starting points are things like random forest or principal component analysis. That's good enough. Because you should know, how far you can go with something that's actually interpretable. So if someone asks you, like a referee, okay, that's a great result, but how does it work? And if you can't answer that question, then maybe that's a problem. And so you want to know, like, how far you can go with methods where you're able to answer that question, and what's the actual the additional benefit to going to a much more uninterpretable approach. Also, you should be aware that adapting modern deep learning methods to a new problem is actually quite hard, and it's very easy. You can spend a couple days, download somebody's code and just put your data into it, and you can easily get results that are worse than a much simpler kind of trivial method. So there's no guarantee that just because someone has published a state-of-the-art result on something which seems kind of similar to what you're doing, it's my experience is that it's always pretty frustrating to just try and adapt one of those existing method to your data, because you actually have to do a surprising amount of work to get even close to the performance that other people were finding. And then of course we don't, we're scientists, we want to create, we don't want to just reuse other people's ideas, and so you'll be tempted as you get into the to say, well, I'm going to, I don't need to just use other people's ideas, I'm going to develop my own brand new machine learning methods. But that is notoriously hard. Okay, the computer science community does not know how to really do that in a systematic way, and that's why we have this grad student descent. So you don't necessarily want to get into that game. However, I think there is a lot of low-hanging fruit, by which I mean there are scientific problems that have never really had any machine learning, kind of the obvious machine learning methods applied to them. So it's good to look for those. I'm sure in your area of research there are outstanding problems where the existing machine learning methods will help. Okay, so some issues to be aware of as you start getting more into machine learning. So as I've kind of emphasized already, deep machine learning is very wasteful of data. That's not a problem if your data is ad clicks or there's an infinite supply of ad clicks. But your data, it might actually be a bit more resource intensive to collect your data. One mitigation is that if there is a branch of machine learning called active learning, not like active learning we do in classrooms here, but it's a technique for learning. And the idea is that you actually use the machine learning algorithm to guide you in collecting your data. So it will tell you, you collect a small amount of data, and this is to solve the problem when the labels are expensive. So you collect a small amount of labeled data, and then it will tell you, and you have a whole bunch of unlabeled data, and it will tell you from the unlabeled data which data would be optimal to get a label for. So it actually will guide you in building up your data set in an efficient way. Another problem is that learned deep models are opaque, by which I mean they're really hard to interpret. So you have to ask yourself, how important is it that you can interpret what the model is doing? It may give you a state-of-the-art result, but does it matter that you have no idea how it's working? And so you want to get a benchmark. How much worse does a more interpretable traditional method perform? Another thing to be aware is that the machine learning algorithm will cheat if you let them. Okay, there's no code of conduct in machine learning. It's they're very effective at exploiting all the available information, and so you've got to be really paranoid about whether your data includes some unintended signals. So I've seen examples where an algorithm just was performing, it was just too good to be true how well it was doing. And then it turned out that instead of really learning how to study the pixels and identify different types of galaxies, what it was doing, it was actually the different types of galaxies had been compressed with slightly different JPEG compression settings. And it just discovered that it's much easier to learn to figure out the compression setting than to actually figure out what type of galaxy it was. Okay, so that's, of course, and it gave great results. But that's not at all what you wanted. And so that'll happen, like timestamps. You have timestamps in your data. Maybe one category was always collected on the weekends, and one was collected during the weekdays, and that's what it'll learn. But that's not at all what you intended. So you got to be really careful. Don't trust the algorithm not to cheat. So. Okay, another issue is that a trained neural network is actually very easily fooled. And so there's an interesting body of research now on what are called adversarial examples. And so basically any machine learning algorithm, there's kind of now a systematic way of coming up with inputs that will fool it in very counterintuitive and surprising ways. So this is an example. This is an image classifier. So there's one image in the training data. So it correctly says, so that's a panda with about 60% confidence. And then we just add to that multiplied by 0.007, so just a tiny little perturbation, this thing which looks like noise. And if you ask it what do you think that is, it says it's a nematode with 8% confidence. Fine. But then when you add those two together, you have something which looks almost identical to the original panda, and yet it says it's a gibbon with 99% confidence. Okay, so I think there's no machine learning algorithm that has been shown to be immune to these types of adversarial attacks. Okay, so depending on how you're going to use your machine learning algorithm, then you've got to be it's got something to be aware of. Okay, so kind of last caution is that a learned model is going to encode the biases in your data. That's kind of what you want it to do. But you want your data to be as unbiased as possible. And it even worse, it can magnify these biases. So if you take the output of one model as the input to another model, then these biases can get even stronger. And there's research that also shows you can be biased on variables that are not in the data set. And so it's not really clear how this factors into kind of scientific research, but there is a pretty growing awareness of the ethics of using machine learning in society. So this is a good, if you want to learn more about this, this is a good starting point. So this is an example here, it's hard to see, but it's a classifier that says whether a face is male or female. And so first thing is that the algorithms, it's comparing algorithms from different vendors. The algorithms are much more accurate for saying on men than women, but also there's even more striking differences for people with darker skin. It does much worse than people with lighter skin. So it's just, that's just reflecting the data set that it was trained with. So it's interesting research there. The link here. So another is in natural language. So language models are learned basically through mathematical relationships, kind of embedding words into a high-dimensional space. Just using linear algebra, you can express relationships like father is to doctor, and then what's the analogy mother is to what. So in general, when you put this into the state-of-the-art language models, what do you think they put there? Nurse. Okay, so that's just reflecting the bias in the data that this was trained with. Okay, so more positive notes. So I think some exciting developments to watch. A good way, once you've kind of got a foundation in understanding the terminology, and then I think think it's fun to just follow along the recent developments with blogs. So one area that is pretty exciting is probabilistic and generative models. We talked about what those were. Those were applications of unsupervised learning. So there's a lot of work with things called normalizing or autoregressive flows. So this is an example here. This is an algorithm called GLOW. And so these images are completely synthetic images. Okay, this was trained on a database, a standard database of celebrity faces, real celebrity faces. And then it's basically able to ingest that and learn a model that can generate new celebrities that have never been seen before. Okay, so I'm not sure what the social value of that is, but what I want you to take home is to think about, well, how? I mean, that's a really powerful thing, right? This is remarkable how well this is working. So how could you use that in your research? Is there some distribution on complex objects, like faces of celebrities, that it would be useful in your research to be able to generate new examples of? And this is kind of the state of the art, how well you can do that. So. And this is a really hard problem because we're very good at seeing faces that don't look right. So another one in natural language. So a natural language model is basically something that can predict the next word in an arbitrary sequence of text. So here's a link, you can try it out. But I put in this paper I'm too lazy to write my papers. I'm just going to have this algorithm generated for me. So then it tells me, it gives me some choices. So it says the most likely thing is present, 12%, or describe or examine. So I can click on one of those, and then it'll give me a choice of the next words. And if I don't want to just click on each word, I'm even lazier. You can use this algorithm. All I need to do is feed in that beginning. In this paper, we, and it will then write out, it will give me 3 paragraphs of coherent English. Okay, so next time you've got a grant proposal to be on a really short deadline. but seriously,
how
so
many machine learning journal articles are real?
there was an article just recently that was about abstracting text, and the abstract of the paper was generated with the algorithm. And you couldn't tell until you got to the end where it said, by the way, this abstract was generated. So how is this relevant? So you should think, well, do you have any data that is, somehow maps onto natural language? So it's like variable length, it has some sort of natural vocabulary, a predefined vocabulary. So then if you have data, so like genome sequences, for example, if you have data that's like that, then there's already a powerful, rapidly evolving field there. And then final example, so something called reinforcement learning. So this allows you to learn a decision-making policy by doing trial and error, usually in a simulated environment, because it's too expensive to do it in real time in a real environment. And the machine learning here is very inefficient. It needs to do a huge number of iterations, but it will eventually learn. So if you've seen a while ago, there was some press about computers that can play various Atari games like Pong. So that was reinforcement learning. So there was just recently a paper from the OpenAI group. I put a link here. And basically what they did is they were able to learn emergent behavior. So it's a simulation which has some people and some objects like blocks, and they learn all these strategies: chasing, fort building, ramp use. And none of that was built in. It just basically the algorithm was just let loose in this environment and able to learn all of these decision-making policies. Again, you think about how that might map to a problem you have in your research. So I've been thinking that this could be a useful way to optimally schedule time on the telescope. So each night you open up the dome and you want to kind of figure what's the best way to sequence the observations during the night. And you can't just kind of do it. It's not a deterministic problem because you have changing weather and conditions and things like that. Okay, so I started with this machine learning cycle, but I think it's important, and this is kind of something that's talked about, to mention what I called the machine learning meta cycle. So that is, really what's the whole process of using machine learning. So first of all, you have to define the problem canvas. Okay? So it's really important to state the problem clearly. So what is the data that you're going to use? What are the labels, if it's supervised learning, that you want to do? And what type of task is this? Is it a supervised task, unsupervised? And it's important to clearly specify the problem. Okay, then you're going to want to review the literature and the available resources. I found that it's pretty hard to apply something that's where you've only got it as a paper, it's just all these equations. It's much easier, and it's kind of it's a pretty big trend now that people are including the code and sometimes even the data on GitHub repositories. So that makes a big difference. Then you need to prepare your data. I guarantee the data you have is not in a suitable format. You'll probably need to coerce it into that tabular structure. You may actually need to collect the data. You'll need to clean your data. There's going to be like invalid values, there'll be missing values. You have to deal with all of that. It's much easier to deal with it in the beginning than try and train your algorithm to deal with it. You'll have to pre-process the data. Generally, things need to be normalized and have zero means and things like that. And then before you go any further, it's really important to collect baselines. So you need to be able to answer the question for yourself and maybe also for the referee. Well, okay, so I'm going to use this fancy machine learning algorithm, but what is just if I just did the simplest thing, what performance would it get? What is the state of the art? And then often it's interesting to know, well, what is the human performance level? So are we trying to do a task that humans are good at and we're just trying to automate it? And if so, what is the human performance of this? So it's important to know those benchmarks so you'll know the results you get, how they compare. So you have to identify what's the most, you've done all of this research before you actually do any machine learning yourself. And now you need to figure out what are the most promising approaches. And you have to just narrow it down to a few, otherwise you're just going to spend too much time exploring each of these. And now you get into the real work, you train the model on your data, you test it, you rinse, repeat, and you spend a lot of time here. But you'll spend less time here if you do these steps carefully. And that's an important message. And then finally you're going to publish, and I implore you to include your code and your data when you publish. That's how the field works. Okay, so finally, how do you get started in all of this? So you have some technology choices that you need to make. So you need to pick a software framework and a hardware platform. So for the kind of more traditional machine learning algorithms, so they're kind of the go-to place for those is this package called scikit-learn. That's kind of one stop for most of that. But then once you get into neural networks and deep learning, there's two competing frameworks. There's TensorFlow from Google and PyTorch from Facebook. So these are both open source projects, so you feel comfortable using either one. So I guarantee whichever one of these you choose, you're probably going to regret it within a year. And that's because, look at the names, Google and Facebook. These guys are competing with each other all the time, and that's a good thing. So it doesn't really matter for the course that I teach here. The first year I used TensorFlow, and then I spent some time with PyTorch, and I said, oh, why was I wasting my time with TensorFlow? And then the second year I did everything in PyTorch. This year I'll probably go back to TensorFlow. So it's I think roughly speaking, if I had to break it down, I'd say PyTorch is more comfortable for kind of research type environments, whereas TensorFlow is better if you really need to do things kind of at industrial scale in terms of using large amounts of compute resources or deploying things on mobile platforms. Another thing to be aware of is that there's a lot of hype around things like TensorFlow and PyTorch. Both of those actually have pretty rich ecosystems, and in particular, one thing that you should pay attention to is what's called probabilistic programming languages. So within TensorFlow, there's something called Edward 2, and within PyTorch, there's something called Pyro, which I think actually comes from Uber, the Uber AI group. And so what these are is they're layers on top of TensorFlow or PyTorch that allow you to really express your problem in the language of statistics, so in terms of probability distribution and random variables. So those are very powerful for really doing statistical inference. And then you also need to choose a hardware platform. So you should always just start with your laptop. You're going to spend, even if you have access to much fancier resources, you're going to spend a lot of time. You're mostly going to be limited by your human brain cycles, not CPU cycles. You can do that on your laptop. When you're ready to actually, when you've got a problem and you need to use it, you need to do things at a scale that your laptop can't handle. So you're going to need some hardware that has a GPUs, graphical processing units, that will accelerate 10 to 100 times the whole process. So now you need to use cloud computing. It's actually very easy to do. So I would recommend, I've used both Amazon and Google Cloud Computing. It's pretty cheap. It's basically pay as you go. So you need to give them a credit card, and then you'll get periodically get unacceptable bills. But the important thing is the numbers are pretty small. So, and in fact, Google also has this thing called Collaboratory. I put a link here. So this actually lets you open up a Jupyter notebook, and you can connect that Jupyter notebook to a kernel that has access to a GPU. So it's not a very powerful GPU. And you can even now with Collaboratory connect to something called the TPU, a tensor processing unit, which is Google's own custom hardware for accelerating machine learning calculations. And then finally, probably a lot of you are using right now kind of servers in your research group, so sitting in someone's lab or in your desk somewhere. And so it's actually fairly practical to buy, or a lot cheaper to build your own personal GPU server. So I did this as a photo of one I have in my office. It's relatively cheap. It's kind of fun too. The main challenge, you're basically just buying a bunch of components online and then putting them together. The main challenge is that this is the GPU right here, is that it needs to be really well cooled. So in this case here, I'm using a water cooling rig, but you don't have to do that. You can also use that good fan circulation. So if you'd like to know more about that, or maybe your advisor has told you you've got to build this computer, you can talk to me about that. Okay, and then finally, what are some good resources to get started with? So, so there's the course that I teach here. So we've done this 2 years now. Next year it's going to be in the catalog as Physics 223. It's called Machine Learning and Statistics for Physicists. But in fact, there's nothing really physics about it. You put your hand up here if you've already taken the course. So there's some people, if you want to ask them about the course, is there anything like too physics specific about it? I don't think so. So if you're interested, you could take that course. It's offered in the winter. There's some great resources online. So I think the Stanford Machine Learning class, CS229, all of the lectures are online. And then Coursera, Andrew Ng has a bunch of different courses available here, and I find them really clear and insightful. And then once you get up to speed, there's a lot of blogs that are useful to follow and help you understand recent developments. I find that when the new papers come out, they're pretty hard for me to understand, and I just wait till someone writes a blog post about it. And, they basically explain how it works and break it down into examples. So it's much easier to keep up with things that way. And then maybe we need a study group in the physical sciences. Right? There's a lot of interest in this, so we probably have a critical mass to have a useful study group just here in the school.
Physical sciences, machine learning, Nexus should be the next item there. Hopefully.
Okay, so thank you.
Looking for some questions?
I was just curious if you could name like one or two of the plots that you'd like to read.
Yeah, I started to think about putting some in, but there's actually quite a lot. Unfortunately, they're low volume, so but maybe that's something we can do. Like if have somewhere where people can post logs they found useful, but I have like a list of 10 or so that I follow. And if you want to contact me later.
Okay, yeah, great.
Just in response, so in general, the machine learning Reddit channel has all the useful blog articles.
Okay.
Just
One channel?
Yeah, people upload the what one using.
Okay. Yeah, I tend to find there's certain authors that I can just click with, like I just like the way they present things, and you can tell they're putting all the care into it.
A lot of science data is really big. Do you know places to share that? Like most of the repositories of libraries are rather small relative to what most people collect and share. What can?
So okay, first of all, so it means most scientific data is not really big by machine learning standards, but I think so. It's not.
Each piece might be really big, even though it's not in pieces.
Yeah. So but okay, but just to be clear, that's not a problem for machine learning. But I think you're asking about how to share it.
Yeah, you mentioned sharing stuff, which I always find.
Right. Yeah. So often you do need to kind of whittle down to a well-defined smaller problem, I think, in order to share the data. And so in my research collaborations, we've been exploring a lot using different cloud services. And what we discovered is that the CPU is actually really cheap, but it's the storage that really you pay a lot for it. So we're struggling with whether it's so it's easy to just push your large data sets to Amazon file servers, but it's actually pretty expensive. So if you've got put it into your research, into your grants, and if you've got the money for it, then that's a great way to have high availability of your data. But I don't think there's a cheap way to. Does anyone actually know more about the ICS archive, like your machine learning data sets? Like, how big a data set can be stored there? But they have a physical sciences area already on the archive, but it's not I think most of the data sets are pretty small. Maybe we could, do you have a couple terabytes we can?
We have Crisp now on campus, and you got a terabyte for free, but you got to pay up for that.
I think PI is only
What about the DVC, that data Git-based versioning system?
I don't know that.
Yeah, Git has this large file system that you can use for. We looked at that on my project, and then decided it was better to do something.
Yeah, this is a site that provides, that's the solution for that, and it is Git-based. The interaction is Git-based. Jason mentioned yesterday at the Git talk, you guys recall that? His slide has some information about that. I'm not sure what the parameters are, how much or how much cost or how much data we put in there.
So are you just interested in sharing the data, or just putting the data from the slide and do some modeling or training? You mentioned sharing data to other PSML. In case you're just sharing data, actually all the UCI person has some unlimited access to Bootcamp. So that actually I probably like 40 kilobytes so far. So far Google did not lose anything. Yeah. So we'll see. Yeah. But actually it's working. So but the thing is that the daily transfer, there's a limit in the data transfer, which is like a 750 or less than 1 terabyte a day. So yeah, you have to keep that in mind when you're using the Google Drive for sharing.
Anyway, thanks, Dave. Hope we'll take a 15-minute break or so, and we'll have Professor